My dear students, welcome to Easy BTech, your guide for BTech and beyond. We are discussing the subject Signals and Systems, and we are discussing about Fourier series and Fourier transform, continuous time Fourier series, continuous time Fourier transform. So in that discussion, and today we are going to see properties of Fourier transform, important properties we are going to discuss. And all of you subscribe, share the channel. It is very helpful to you. I am sure it is very helpful to you. Let's start our session, properties of Fourier transform. So in the previous session we have covered some of the properties. Still we have remaining properties in Fourier transform that we are going to discuss. So we are going to discuss conjugate property. We are going to discuss now conjugate property. Conjugate property. So first we discuss the definition, then we do proof. All properties are proved with the help of Fourier transform definition only. This point please remember. So the definition is, if x of t Fourier transform is x of omega, x of t Fourier transform is x of omega. Conjugation means x star of t means x of t conjugation, complex conjugation is x star minus omega. So this is the property. X of t signal, its Fourier transform x of omega, its complex conjugate is x star of t, the result is x star minus omega. So see the proof, this property proof. We know Fourier transform of a signal x of t. Fourier transform of a signal x of t is equal to x of omega is equal to integral minus infinite to plus infinite x of t into e to the power minus j omega t dt. Right? This is the first line whatever we have, x of t Fourier transform. Now the second line I am going to take. What is the second line in the statement or in the definition? X star of t Fourier transform. So Fourier transform of x star of t is equal to, so how to write the Fourier transform of x star of t? As like x of t only. So x of t is signal, here in the integral x of t we take. Now x star of t is the signal now, so in the integral minus infinite plus infinite, here x star of t, that's all, e power minus j omega t dt. Is it right? Then I am going to simplify or modify this integral. So I am writing like integral minus infinite plus infinite x of t e to the power, here we have minus j, I am writing as plus j omega t dt whole star. I am keeping star for the total. So if you send a star inside, then we get the same above integral. Okay, right? Now here we have plus j in the power. That plus j I can write as integral minus infinite plus infinite x of t e to the power minus j and minus omega t dt whole star. Right or not? We can write plus j as minus j and minus omega, minus into minus plus again. So if you observe this integral now, the bracket, if you monitor or if you observe, it is like Fourier transform formula. Right or not? Compare the Fourier transform integral and this integral. You just do comparison. We can understand. Just do comparison. So after comparison, what we can say? The integral, this integral is x of minus omega. In the place of omega we have minus omega, and we have star, that is as usual. So star is as usual, that's all. So finally we got Fourier transform of x star of t is equal to x star minus omega. X star minus omega. Very, very simple. Next, another property we are going to discuss. Convolution property. Very, very important. Convolution property. Very, very important property. So we have time convolution and frequency convolution. Okay. So first we discuss time convolution. After that we discuss frequency convolution. Okay. So what is time convolution? See the statement, if or definition, x1 of t Fourier transform is x1 of omega. x1 of t is the one signal, its Fourier transform x1 omega. x2 of t another signal or second signal, its Fourier transform is x2 of omega. Then Fourier transform of x1 of t convolution x2 of t. Here star symbol or star mark, what we call convolution. Okay, so this is the time convolution because both the signals are in time domain. x1 of t convolution, x2 of t Fourier transform. So Fourier transform of x1 of t convolution x2 of t is x1 of omega into x2 of omega. So by this line we can say the point. What is the point is convolution in time domain. Convolution in time domain is equal to multiplication in frequency domain. So that point I am writing here. The line says that, or this property says that convolution in time domain is equal to convolution in time domain is equal to multiplication in frequency domain. Here we have dot, that is multiplication in frequency domain. Multiplication in frequency domain. This we are going to prove now. Multiplication in frequency domain. The proof is very simple. So first of all we should know what is convolution meaning or convolution definition we have to know. Then we apply Fourier transform. Right? So first I am going to say what is convolution. So convolution is x1 of t convolution x2 of t is equal to integral minus infinite plus infinite x1 of tau into x2 of t minus tau d tau. x2 of t minus tau d tau. So we are multiplying x1 of tau, x2 of t minus tau. After that multiplication we are doing integration area. So convolution gives the common area between x1 of t, or x1 of tau, x2 of t minus tau, or x1 of t, x2 of t, common area between two signals. The common area between two signals is going to do. And this convolution is important. This is important to find output of convolution is very important, because using convolution we can find output of LTI system, linear system. Output of the linear system is calculated with the help of convolution. Output of the linear system. So convolution is very, very important. So here just you remember convolution integral or convolution formula definition. Now this is the convolution meaning. Okay, Now we know generally Fourier transform formula, Fourier transform of a signal x of t is equal to x of omega is equal to integral minus infinite plus infinite the signal x of t into e to the power minus j omega t dt. Right? So here we want Fourier transform of x1 of t convolution x2 of t. x1 of t Fourier transform of x1 of t convolution x2 of t. So how to write it? Fourier transform of x of t is here x of t. Now Fourier transform of x1 of t convolution x2 of t. Please understand, Fourier transform of x1 of t convolution x2 of t. So integral minus infinite plus infinite x1 of t convolution x2 of t, okay, into e to the power minus j omega t dt. That's all. So already we know the convolution meaning here, that we are going to take and substitute. So by taking the convolution meaning, so is equal to integral minus infinite plus infinite. What is the convolution meaning? Again integral minus infinite plus infinite, plus infinite. So this is the convolution meaning. For clarity I am using red color. Minus infinite plus infinite x1 of tau into x2 of t minus tau d tau. This is the only convolution meaning, and remaining into e to the power minus j omega t dt, So here we have two integrations. One integration is with respect to tau and another integration is with respect to t, right? Double integration or two integrations we have. So I am going to do I am going to arrange like integral minus infinite to plus infinite, x1 of tau, again integral minus infinite to plus infinite x2 of t minus tau e to the power minus j omega t dt d tau. Okay, so this is the t integration. So I am writing t terms in the middle integral. Again the total is integration by tau. Okay, so now this is the arrangement we are doing. We can write like this. Okay, now let t minus tau is equal to, let t minus tau is equal to some variable p. The t minus tau I am taking as a p. From this t will become p plus tau and dt will become, what is dt? Will become dp, because tau is a constant. So dt will become dp. Then lower and upper limit, if you see lower limit, upper limit, so what is the lower limit of p? Is equal to lower limit of t minus infinite minus tau, it will become minus infinite, and upper limit, so p is equal to, what is the upper limit here? Infinity. So infinity minus tau, again infinity. Infinity is a large number, so nothing happened to infinity. Infinity is infinity. So these all we are going to take in this integral. We are going to substitute here. So let's go to next step. So is equal to integral minus infinite plus infinite x1 of tau, again integral lower limit is minus infinite plus infinite x2 of p, t minus tau we have taken as p, so e power minus j omega p plus tau dt, dt is the dp and d tau. So again we have two integrations. Now I am going to separate them. So one integration is with respect to p, one more is with respect to tau. So p integration, p terms, in tau integration, tau terms. That I am going to do, nothing else. So integral minus infinite plus infinite x1 of tau. So here if you observe this exponential term, e power minus j omega p, e power minus j omega tau, right or not? So I am going to take here e power minus j omega tau. I am writing here, this is completely tau, so d tau, all tau terms. And next thing, integral minus infinite plus infinite x2 of p e to the power minus j omega p, here minus j omega p, that dp. So all p terms, right? So if you observe these two, the first integral says that, what is the first integral says that, and what is the second integral says that. What is the meaning? Fourier transform formulas, like Fourier transform. So the first integral is Fourier transform of x1 of tau, right or not, into the second integral is Fourier transform of x2 of p. So how can we write Fourier transform? How can we represent x1 of omega into the second one x2 of omega? So this is the proof. So convolution in time domain is multiplication in frequency domain. That is a point here in this property. Convolution in time domain is equal to multiplication in frequency domain. Let's take next one. The next is frequency convolution. So convolution in frequency domain. So what will be the result you get now if you take convolution in frequency domain? Multiplication in time domain we get. So that we are going to discuss now. Frequency convolution. Frequency convolution. Right? So what frequency convolution is saying? Frequency convolution. What it says? Frequency convolution. Convolution in frequency domain is multiplication in time domain. So I am going to write the property statement. If x1 of t Fourier transform is x1 of omega, x2 of t Fourier transform is x2 of omega, then convolution in frequency domain means x1 of omega convolution x2 of omega, x1 of omega convolution x2 of omega, x1 of omega convolution x2 of omega, here by 2 pi. So with the left hand side we get multiplication x1 of t into x2 of t, x1 of t into x2 of t. This is the property saying. So left side x1 of t into x2 of t. So convolution in frequency domain will become multiplication in time domain. That is the point here. The point is convolution in frequency domain. Convolution in frequency domain is equal to multiplication in time domain. Multiplication in time domain. So this we are going to prove now. Very simple. Again we take the convolution definition. So here we use inverse Fourier transform formula. To prove it, we are going to use inverse Fourier transform formula. See the proof. So first we take convolution. So convolution of x1 of omega, x2 of omega, x1 of omega and x2 of omega, that is x1 of omega convolution x2 of omega, x1 of omega convolution x2 of omega. So how to write it? Same, integral minus infinite plus infinite x1 of lambda x2 of omega minus lambda, okay, d lambda. So previously we have written x1 of t convolution x2 of t. In the same way I am writing. So previously x1 of t convolution x2 of t. The integral minus infinite plus infinite x1 of tau. So previously x1 of tau, here x1 of lambda, x2 of t minus tau, d tau. So now here x2 of omega minus lambda d lambda. In the same way I am writing, right? So this we want x1 of omega convolution x2 of omega, and we know inverse Fourier transform of x of omega is equal to x of t is equal to integral minus infinite plus infinite 1 by 2 pi you get here. So 1 by 2 pi integral minus infinite plus infinite x of omega e to the power j omega t d omega. This is the inverse Fourier transform formula. So I am going to use this now. So inverse Fourier transform of this, inverse Fourier transform of x1 of omega convolution x2 of omega, inverse Fourier transform of x1 of omega convolution x2 of omega. How to write? As like inverse Fourier transform of x of omega. So here x of omega, in integral we have here x of omega, here x1 of omega convolution x2 of omega. So in the integral x1 of omega convolution x2 of omega, that's all. So if you understand this step, remaining is easy. Into e to the power j omega t d omega. So this already we know. We discussed this convolution, right? So I am going to take that and substitute here. x1 of omega convolution x2 of omega. Let's have substitution. Then is equal to 1 by 2 pi integral minus infinite plus infinite 1 by 2 pi integral minus infinite plus infinite x1 of lambda. This I am going to substitute, convolution I am going to substitute. So again we get integral minus infinite plus infinite x1 of lambda x2 of omega minus lambda d lambda, right? Convolution we have substituted e power j omega t d omega, and in the statement we have by 2 pi, right or not? In the statement, if you go to statement or definition, frequency convolution definition, we have by 2 pi. So that by 2 pi, here again by 2 pi, it will become 4 pi square, right? So I am going to take that outside 4 pi square. In the statement by 2 pi is available, so I am considering that by 2 pi. Now here again we have two integrations. One integration is with respect to lambda d lambda, that is integration with respect to lambda d omega with respect to omega. So I am going to arrange the integrals as like lambda terms and omega terms. So see that arrangement, 1 by 4 pi square integral minus infinite plus infinite here lambda terms I am taking. So that is x1 of lambda, right? X1 of lambda, and another integral minus infinite plus infinite x2 of omega minus lambda e to the power j omega t d omega. So all omega terms are included in this integral d lambda, right? Yeah, x2 of omega minus lambda e power j omega t d omega d lambda. Now I am going to take this bracket. Let omega minus lambda is equal to some variable p. From this, omega will become p plus lambda. Omega is equal to p plus lambda, and d omega will become dp because lambda is a constant. D omega will become dp. And what about lower and upper limits? So the lower limits, what is the p we have? Omega minus lambda. So omega limits minus infinity, lower limit is minus infinity. So p also lower limit minus infinity. Upper limit of p. So what is upper limit of p? P is equal to, what is p? Omega minus lambda. What is upper limit of omega? Plus infinity. So p is upper limit also plus infinity. So all these we are going to substitute in the above integral. Then we have, these are all I am going to substitute here. So just to do that substitute, do that 1 by 4 pi square integral minus infinite plus infinite x1 of lambda, again integral minus infinite plus infinite, lower and upper limits same, x2 of p e to the power j, here omega is equal to p plus lambda, so j p plus lambda t, and d omega is dp, d omega is dp, right? J omega t, d omega is dp d lambda. Okay, now we are going to separate these integrals again. Lambda terms, p terms we have, so I am going to separate them. So 1 by 2 pi integral minus infinite plus infinite x1 of lambda e to the power, here j lambda t d lambda, completely lambda integration this is, and into again 1 by 2 pi, we have 4 pi square, right or not? So 1 by 2 pi, 1 by 2 pi we can write, and the second integral minus infinite plus infinite x2 of p e to the power j pt, here I am writing j lambda t j pt, in the power we have plus dp. Now if you observe carefully what this integrals indicates, 1 by 2 pi, again 1 by 2 pi, inverse Fourier transform formulas, right? So the first one indicates inverse Fourier transform of x1 of lambda, and the second one indicates inverse Fourier transform of x2 of p. So already we know inverse Fourier transform, it converts into time domain, so x1 of t into x2 of t. Multiplication we got, right or not? So convolution in frequency domain will become multiplication in time domain. So finally what we can write is, x1 of t multiplication x2 of t, its Fourier transform will become convolution in frequency, x1 of omega convolution x2 of omega, and here by 2 pi. So this is the statement and we proved. Okay, let's go to another one, another important, Parseval's energy theorem. Parseval's energy theorem. So what it is, first we see what is the definition, then we have proof. Parseval's energy theorem. So this theorem is saying that integral minus infinite plus infinite mod x of t whole square, magnitude of x of t square will become 1 by 2 pi integral minus infinite plus infinite mod x of omega or magnitude of x of omega square d omega. Very important relation. This is a relation. So to calculate the energy of the signal, left side indicates energy of the signal. Integral minus infinite plus infinite magnitude of x of t square means energy. So this energy we can do using its Fourier transform. X of t Fourier transform is x of omega. So by doing the integration and square and divide by 2 pi, we get the energy of a signal. This is Pascal's energy theorem. So see the proof. This proof we can do using inverse Fourier transform formula. So we know inverse Fourier transform, f inverse of x of omega, inverse Fourier transform, f inverse of x of omega is equal to small x of t is equal to integral minus infinite plus infinite, right, x of omega e power j omega t d omega. This is the inverse Fourier transform formula. So let's take LHS, this LHS, and 1 by 2 pi also there. 1 by 2 pi. So take that 1 by 2 pi. In inverse Fourier transform we have 1 by 2 pi. 1 by 2 pi. Now this one LHS, left hand side, what we have left hand side? Integral minus infinite plus infinite magnitude of x of t whole square dt. So this magnitude x of t whole square we can write as integral minus infinite plus infinite x of t into x star of t, complex conjugate of x of t dt. So this magnitude of x of t whole square we can write as x of t into x star of t. Okay. Now here we have x of t. Now I am going to write x star of t from x of t. So what is x star of t? Complex conjugation of x of t. What it will become? 1 by 2 pi and integral minus infinite plus infinite x star omega, we are applying complex conjugation, and e to the power plus j will become minus j omega t d omega. Okay. So this x star of t I am going to substitute in this integral. So do that substitution, we get the result. So 1 by 2 pi is outside and integral minus infinite plus infinite, and this x of t is as usual, only x star of t we are going to write. So what is x star of t? 1 by 2 pi, already I written 1 by 2 pi. Again integral minus infinite plus infinite x star omega e to the power minus j omega t, right, d omega, right. This is the x star of t and dt. So here we have dt. Now I am going to arrange these terms like 1 by 2 pi integral minus infinite plus infinite, here t, and here e power minus j omega t dt. So all those I am going to write here, x of t e to the power minus j omega t dt. Okay, x of t e to the power minus j omega t dt. Again we can write the integral x star, so integral minus infinite plus infinite x star omega and this total d omega, and outside we have 1 by 2 pi. Just I am arranging the terms like this. Okay, so all t terms, then integration with respect to omega. So if you observe this middle integral or second integral, it is like Fourier transform formula. Exactly, right or not? The circle. So Fourier transform of x of t we can take as, how to represent capital X omega. So the total this red color integral is capital X omega. Now come to the next step. 1 by 2 pi integral minus infinite plus infinite x star omega into x of omega d omega, right or not? So x star into x, magnitude of x whole square. So 1 by 2 pi integral minus infinite plus infinite magnitude of x of omega whole square d omega. This is the proof. Simple. Only x of t, inverse Fourier transform formula, and magnitude square we can write as x into x star, and x star we have taken, substituted, and I arranged terms like this, arranged integrations like this. This integral integrates capital X omega, then x star into x omega d omega. X star into x is again magnitude of x whole square. This is the Parseval's energy theorem. Okay, so by this we have completed properties of Fourier transform. Very important for examination. Please watch videos, share the channel. Thank you students. Thank you very much.